last session of the day. Last thing I've got to review, or last of my notes that I've got to review for the day. At least of the notes that I've taken notes on in my computer. Everything else I need to review from my materials, mostly for anatomy. All right, first we have phys and histo. Hypoxemia is low blood oxygen. Compare that to hypoxia, which is low tissue oxygen, low oxygen in the tissues. Some causes of hypoxemia are low inspired O2, right to left shunting, hypoventilation, diffusion impairment, and VQ mismatching. Ventilation, whatever Q is, I forgot. Okay, so starting off with the uncommon causes of hypoxemia. Low inspired O2. You're not getting enough oxygen, plain and simple. It can be due to being high in the mountains, or being in space. I don't know. It's pretty much self-evident. You know, you start getting dizzy as you're up in Mount Everest or something like that. And this is an easy fix because you just give them an oxygen mask, supplement the oxygen, fixes the problem. Right to left shunting is where blood doesn't pass through the lungs properly, so it doesn't pick up the oxygen in the lung. It's easy to find because it's typically only found in neonates, which means very, very young animals. And I'll bet it can be caused, hey, how's it going? I'll bet it can be caused by the retention of fetal structures in the heart. No. Well, maybe. I don't know. Because, I mean, why would it be only in young animals? Doesn't make sense otherwise. Anyway, more common causes of hypoxemia are hypoventilation. You're not breathing enough. You're not exhaling oxygen, or CO2. And so by definition, if you've got hypoventilation, hey everybody, if you've got hypoventilation, you also have hypercapnia. What is hypercapnia? That is too much arterial carbon dioxide. So you're not getting rid of the carbon dioxide. Sometimes this is just voluntary hypoventilation. Sometimes you hold your breath, and then you become hypercapnic. But it can be accompanied by other causes. A lot of neuromuscular diseases cause that. And so, anyway, next one is diffusion impairment. It's more common, but it doesn't often occur alone by itself. It's usually a minor factor. The exception is during strenuous exercise in extremely fit athletes. So diffusion impairment is like where the blood is going through the capillary too quick that it can't get enough carbon dioxide from the lungs, or oxygen from the lungs, I think, to take to a tissue. Does the blood just go clockwise? No, not necessarily. And, clockwise, you'd have to be talking about, which way's the clock facing anyway on the body. No, it's a lot more complex than that. Hey, guest, how you doing? It's generally speaking, blood goes from the heart through arteries to tissues. Then it goes from tissues through the veins back to the heart. And these veins are all over the body. There's veins up here, veins in here, veins in here, arteries in here, here. Yeah, it's a cycle. That's right. Circulatory system. And but there is one exception. The pulmonary veins take oxygenated blood to the heart, and the pulmonary arteries take deoxygenated blood from the heart to the lungs. Every other vein in the body takes deoxygenated blood back to the heart. Every other artery in the body takes oxygenated blood from the heart to the tissue. So that's one exception in the lungs. Anyway, diffusion impairment is basically where you just can't. You're working your body super hard. Like in the case of an extremely fit athlete, and you pass out because your blood isn't able to get oxygen quick enough and drop off carbon dioxide quick enough. You're just working too hard, which isn't necessarily a result of, hey, how's it going? It's not necessarily a result of disease. I mean, if you're an extremely fit athlete, that's like the opposite of disease, right? So, but the most common cause of hypoxemia is VQ mismatching. So, yeah, that's a good way of putting it. Like the blood's rushing, but it's going so fast that, it doesn't even have time to pick up the oxygen or drop off the carbon dioxide. Yeah. VQ mismatching. VQ mismatching is basically blood not getting where it needs to go on a microscopic level. For example, if you're doing surgery on a dog, usually whenever we're doing surgery on dogs, we flip them over on their back. Their body's not used to being on their back. They're used to being right side up, right? And so their whole body is adapted for pumping blood while they're right side up. If they're on their back, that changes things a little bit. Now it's even more pronounced in larger animals like mules, horses. For example, there was a test done by a scientist back in the day. He had basically pet mules. He would put them on their side. They were fine on their side, but whenever he put them on their back, they'd become hypoxemic. Again, hypoxemia. Sorry. All those words mean not enough oxygen in the arteries. Now, hypoxia is different than hypoxemia. Hypoxia is not enough blood in the tissues, or not enough oxygen in the tissues, sorry. Hypoxemia is not enough oxygen in the blood, in the arteries. Yeah, okay. But if an animal's on their back, their lungs adjust. There's all sorts of things the body does to adapt. Our bodies are very fearfully and wonderfully made, as the Bible puts it. Okay, ideal VQ matching is expressed as a ratio of 1. Anything greater than 1 is alveolar underperfusion or overventilation. You're breathing too much, or the alveoli are not perfusing enough. And if it's less than 1, the alveoli are perfusing too much, overperfusion, or you're not breathing enough, underventilation. If it's greater than 1, that's again overventilation or alveolar underperfusion. There's no hypoxemia in that case. If it's lesser than 1, that's underventilation or alveolar overperfusion. That is going to be hypoxemia. Not enough oxygen in those arteries. Respiratory failure. So if the respiratory system is successfully eliminating CO2 from the body and absorbing O2, I look 12. Thank you. Thank you, I appreciate that. And the work of breathing is minimal, doesn't require much energy, then I would say your respiratory system is adequate. It's evaluated by the success and achieve. Yeah, because it's eliminating the CO2, getting the oxygen to the tissues, and all the while it's efficient in doing so. That's all you can really ask for with your lungs. But it doesn't need to be complicated. There's sensors like carotid bodies that we talked about earlier, respiratory centers. There's also externally visible indicators like respiratory rate and effort. And then there's drawbacks of these systems, though. They're not really specific for the respiratory system, and they're not quantitative. But there are precise ways to evaluate respiration, like arterial blood gas analysis. That's where you take blood from an artery, just left the lungs, and you test it. You see, well, is this arterial blood high in oxygen? Is it low in oxygen? Just try and find out. Hypoxemia doesn't necessarily mean respiratory disease always. I mean, in the case of, hey Blitz, how's it going? I ate as well. I took like a 2-hour break, so anyway, it's good to have you back. Hypoxemia doesn't necessarily mean respiratory disease, because again, it can be voluntary, where you're holding your breath, so you're not getting enough oxygen in your blood. But hypercapnia, which is too much CO2 in your blood, is always due to respiratory failure, because it's due to hypoventilation. Again, hypoventilation that's that component that is can be voluntary. I mean, I could just stop breathing. That is, by definition, hypoventilation. Hypo meaning less than, in this case, less than adequate. Ventilation meaning ventilation, breathing, right? Less than adequate ventilation. Hyperventilation, you've probably heard of that before. Hyperventilating. If someone's hyperventilating, they're like, they're going crazy, breathing too much. Everyone's heard of that, But hypoventilation is the opposite. Anyway, So air in the inspired air contains about 20% oxygen and 80% nitrogen and not much else. There's other gases, of course, hydrogen, helium. But at sea level, the partial pressure of oxygen is about 152 millimeters of mercury. Yeah, carbon dioxide. Yeah, that's another component of air for sure. The rule of thumb is that every 100 meters of elevation you go down, go up, it's a decrease of 1 millimeter of mercury of pressure of oxygen. So, for example, if at sea level it's 152 millimeters of mercury, which is just a way of measuring pressure, kind of like atmospheres or psi. If you went up to 100 meters above sea level, you'd have 151 millimeters of mercury. So that's just one thing there. You can't directly measure alveolar air, though. You can calculate it, however. If you have less than 100 millimeters of mercury of O2, it's most often, more likely than not, hypoxemia. Normal CO2 is around 40 millimeters of mercury. If it's lower, then it's probably hypocapnia. If it's higher, it's hypercapnia. Less atoms tapping and holding each other and stuff. Yeah, the higher you go, the less dense. That's exactly right. That the air gets. There's literally just less molecules bumping into each other. That's why your ears pop. That's because the pressure inside your head's literally trying to come out. It's kind of scary. But then you get acclimated to it, you swallow or you chew gum, something like that. But there's also less oxygen to inhale. So that's why it's like that. All right, see you later, Blitz. Yep, alveolar air equation. Yeah, it needs to be warmed. The air you breathe in needs to be warmed and humidified. 100% humidification. Nitrogen ain't no big deal, right? It's 80% in the air we breathe, and yet we're still alive. So inhaling nitrogen doesn't seem to have a negative effect. I mean, the only time it would is if, one, you're inhaling only nitrogen, then you might pass out because, where's the oxygen? And two, if you're scuba diving, you go too deep and then you come up super fast. That's something you're not really supposed to do in scuba diving. It's called, what'll happen is you'll get something called the bends, BENDS, bends. I think that's what it's called, bends. And what that is literally the gas or there's nitrogen in your blood because again, that's what you're inhaling. And it's like bubbling up. So it really hurts, I bet. You're getting a bunch of air in your arteries or your blood vessels, basically. Spooky. Here's an interesting thing. For every molecule of oxygen burned while metabolizing carbohydrates, you produce one carbon dioxide molecule. But for every molecule of oxygen burned while metabolizing fat, you produce 0.7 molecules of carbon dioxide. for each oxygen. This is veterinary medicine, so for animals. So that I would say that lends credence to the argument that fat is a more effective fuel, and a more efficient fuel at least, than carbohydrates, but that's just my opinion. Um, yep, arterial O2. 0.85 is the middle of the road, so you'd most likely use that in certain calculations. And then dogs. Dogs are very, very good. Very efficient animals. Very good at delivering oxygen. No, I'm not vegan. I am not vegan. I'm the very opposite. I'm carnivore, actually. Doing a carnivore diet. And, I mean, there's sometimes I might have a, cheeseburger with a bun or whatever. I might have an ice cream. But, well, if you remove the sugar and stuff from the ice cream, it's technically carnivore. But most of the time I eat. I mean, if I had it my way, I'd be eating ribeye steaks every day. But I'm not a millionaire. So right now I'm just eating like ground turkey and eggs. So that's what I've been eating every day for the past week or so. Now carb cravings are strong because I've had some diet cheat days recently, and once you have a cheat day, you're like, oh man, those carbs. I need the carbs. It's crazy. You get sugar addiction. I don't like it. Okay, next. Immunology. Cell activation. Right? Is this the one I'm on? Yeah. Cell activation. T cells are made in the bone marrow and they go to the thymus to develop. B cells made in the bone marrow, they experience negative selection in the bone marrow. Dendritic cells made in the bone marrow, present all over the body. Then they go to secondary lymphoid organs all the time. Secondary lymphoid organs are tonsils, what is that? Oh, lymph nodes, the spleen, I think, and then Peyer's patches, however you say that. I already went over all this. Lymph node has a sinus. Yeah, they've got a cortex, medulla. Yep. Kind of like a kidney or a spleen. Then there's something called an immunologic synapse. That's where like a T cell has a TCR that's attracted to a peptide on an MHC molecule. And then that T cell binds to the dendritic cell that is acting as the APC. I don't know. I need to study this a lot more. But I'm just trying to get this over with. I've been doing this for hours already. And immunologic synapse, cell activation, ligand, second signal. It's just a bunch of hoopla. Cytotoxicity of CD8s are cytotoxic. CD4 is helper T cell. So here's a thought. If I wanted to eat a steak, well, that steak is not my tissue, and so it's an antigen. A T cell is a thymus cell. It's actually, they're made in the bone marrow, then they go to the thymus to mature. It is it's a part of the adaptive immune system. They are immune cells that basically they've got memory, like they will, I don't know, I'm sorry, I'm trying to like recall everything I've learned. So they need peptides of antigens presented to them by MHC molecules, which are major histocompatibility complex molecules. And they'll basically just do immune response based on that. And they've got memory, meaning that if they were to experience that same antigen, well, they've had previous experience, so they'd be able to take it out quicker the next time before a problem ensues. Yeah, we're talking about immunology right now. White blood cells. Yeah, all the lymphoid or lymphocytes. Yeah, white blood cells. COVID and stuff. Yeah, I mean, that's how our body fights against diseases like that in the absence of vaccines. What are vaccines? Vaccines are literally just antibodies, I think. I think they're just pre-made antibodies that we get access to from an injection or whatever it is, a pill. I don't know. I don't know if there's any pill vaccines yet. That'd be pretty cool. I don't like needles. B cell. Hey Cole, how's it going? Good to see you. I'm doing okay. How about you? What is the role of positive selection in T cell development? To ensure T cells can recognize self-MHC molecules. During B cell ontogeny, what is the correct order of immunoglobulin gene expression? Heavy chain rearranges first, followed by light chain. Which surface marker is expressed on pre-T cells during thymic development, allowing progression beyond the beta chain rearrangement checkpoint? Pre-T alpha. Thanks, Cole. I appreciate that. Thank you. What happens to B cells that strongly recognize self-antigens in the bone marrow? They undergo receptor editing or apoptosis, otherwise known as central tolerance. How do the selection processes of B cells and T cells differ? T cells undergo both positive and negative selection, while B cells primarily undergo negative selection. And then which is the correct sequence of thymocyte developmental stages during T cell maturation in the thymus? Double negative to double positive, and then to single positive. And that's it for the day. Finally, I've been doing I did 6 videos today, or streams technically, but I ended them and started new ones so that people could go back and watch those, and so I could take breaks. But I'm finally done, so now I can study anatomy for 2 hours. Yep, 2 hours starting now. Thanks guys for watching. Yep, vet school's hard. Maybe I'm trying to keep up with these, but I'll probably do 2 more videos tomorrow, and then from then on it should be 1 video a day. I don't know if it'll be tomorrow or if it'll be Monday, but I'll just do one video a day after that, and yeah, I'll try and engage with my audience. So thank you guys. Thank you for watching. See y'all later.